Hello everyone. I'm recording this video to make some comments about practice 5 of the subject. Practice 5 and practice 6, that are the two remaining practice that you'll have to do, are going to be about digital systems. So we are going to use DITS, this software. This is a simulator of digital systems. We are not going to make real assemblies of circuit, physical assemblies. We are going to work only with the simulators. So, well, I gave you here an example of how to use DITS that I recommend you to see the video and to try these examples. And well, I'm going to go to the practice 5 document that is already available, and you have it here. In practice 5, you are going to make a decoder of a 7-segment display. So you are going to have as an input a BCD number, and you have to convert this BCD number in functions to activate a 7-segment display. As you know, this is a typical 7-segment display, so you have all this output. Each segment is an output. We are going to have as well the digital point, the decimal point, that we are not going to use. We are going to have this decimal point always off. So you have to implement all these functions. How are you going to implement these functions? It is going to depend of your ID number. If you are working in pairs, select the ID number of one of the members of the pairs. So you are going to take your ID number, you are going to sum all the digits, and you are going to divide the result of the sum by 7, and you are going to use the remainder. You can use directly the mod operation. The remainder, as you know, is going to be between 0 and 6. So according to the result you have, you are going to go to this table and locate your row. If you are, for example, if you got a 0 in the remainder, you are here. So you have here specified how to implement all these segments. For example, segment A, that is here, is going to be implemented with a minimal sum. Segment B with a minimum product. Segment C using a minimum NAND implementation. Segment D a minimum NOR implementation. Here a MUX 4:1. F segment a MUX 16:1. And G segment using a decoder. You have here the legend with the explanation of each of the columns. So depending of your ID number, you are going to be in one row or another, and the implementation of your function is going to be different. So you have to resolve this analytically in paper, okay? And before coming to the laboratory. And this way is not recommended. This way is compulsory, and I want to make this clear, because if you haven't uploaded the analytical solution before coming to the lab, your practice is not going to be corrected. So you have a 0. Because it's impossible to go to the lab and implement this in the simulator if you don't have the solution previously. So it's compulsory. Well, you here in the document you have the truth table to be filled. It's quite easy. In fact, well, we started in class to fill the truth table, but it's quite easy. For each combination of the BCD number, you have to make the shape of the number using the segments, activating the segment for each digit. The decimal point is going to be always 0. It's going to be deactivated. In fact, you have here these constraints. The combination that we are going to use are those from 0 to 9, a digit in BCD codifications. The decimal point is going to be always off, and well, this is how you are going to implement each function. That is this thing of the table I just told you about. So you have here the truth table, and according to your ID number, you are going to use the minimal sum in the segment that correspond to your ID number in the table. Minimal sum, minimal product, Here you have the kernel map that you can use to minimize and to extract the logic function. So you are going to have here the kernel map of the segment. You extract the kernel map from the column. Here you'll have your logic function, and here you'll have the circuit diagram. For example, in the NAND gate, you are going to use NAND gates. Here, in the minimal product, you can use AND and OR gate, and here again AND and OR gate. Do you know how to do this before from the subject? So you have here the implementation, the analytical implementation of all the segments. So you have to upload before coming to the lab this practice document with all of this filled. If you have doubts, obviously write to me a message, send me a message, ask me. I'm here to help you. Okay? It's my work. Don't be shy about this. I'm going to be really pleased to help you if you have doubts. But it's important to have this uploaded to the campus before your official session. Once you have this, what you have to do is to implement your functions in DITS. You should know how to do this if you have made the sample that I uploaded. I'm going to show you my implementation that was for remainder 0. I obtained this. You have to be careful and organized when doing this. These are my implementation for each segment, and here I have my here I have my input. I chose clock's input using the frequency to distinguish between the input, and because it's easier to use this that using switches. If you simulate this and it's properly working, you can simulate this. You have to press enable clock animation, and you have to put here 0.5 Hz, or a really low frequency. This is the frequency to pass from one combination to other of the truth table. So you have to put this quite slow in order to allow you to see the result in the output. So if I simulate, I have here, as I told you, all the combinations. You can use this to check the output for all the segments. Well, in fact, you have here the binary number summarized. But this is a way to do it, and you'll have to do it in the practice using the chronogram simulation. But just to check that the circuit is working, you can select the start animation here. So you are going to see how your 7 segment changes as the combination change in the truth table. From 9 on and on, we have don't care conditions. So this is garbage. We are not interested about what happens for combination higher than 9. So it doesn't matter. But from 0 to 9, you have to stay in this. If you change this, the combination are going to change faster. So my recommendation is that you obtain the analytical resolution, upload to the virtual campus once you are sure that it's okay, and try to work with this at home. You can do this at home. You don't have to come to the lab to do it. I recommend you to do, if not all at home, as much as you can at home, and use the lab session to solve doubts, etc. Because before uploading the DITS files to the tags in the virtual campus of the laboratory, I'm going to check that your circuit is working, and I'm going to check pair by pair in every lab station that your circuit is working. I can ask you about any of the implementation, so don't copy because I'm going to ask you. In fact, don't copy my implementation because I'm going to ask about it. So, well, when you have this, you can do the following. This is the converter that I have done between the input MBCD and the 7 segment display. This is the decoder. all of this for every segment. But if you read the practice document, we can build a block using all of this, so we can abstract all of this and not implement all the gates every time we need this decoder. I'm going to show you this because it's easier to understand if I show you an example. This is my block. This is my block. The block is the same as your circuit, but instead of adding the input and here directly the segment display, you are going to add input pins and output pins. In fact, when you want to create a block, you have to make new block. When you make a new block, you don't have here input, you have input pins and output pins. So you copy from your previous decoder all but the input and the output, all of this, in the new block, and you add pins. So when you save the block, you can use it as an element of the circuit. For example, I create a new DIT using the block. Now I have the 7-segment in play, my input, and the block. Inside the block is all the logic and combinational block that I used. And I can simulate this and it's going to work. How do you add to the circuit the block you created before? You have to add a custom component. We can check that it's working. A custom component was let me check here. You create a circuit block element, so you can select it from here, and this block is going to appear, and this block is exactly this thing that we created here. If you have doubts about this, you can ask me, or we can see it in the lab. But make sure that at least this works, okay? And well, in the laboratory session, if you look at the documents of the practice, you have to upload this file, the one of the circuit. This is the one of the block, and a capture, a graphical capture of the simulation that is here. Do you know how to simulate the circuit using the chronogram? And that's all. So check the calendar when is your official session, and make sure that you have the analytical solution before coming to the lab. And this is all. If you have questions, just ask.